Hi guys, in this video we're going to look at the concept hybridization. After having done so, we will apply this concept of hybridization in looking at the shapes of simple organic compounds such as ethane and ethene. This will suggest we are going to be looking at the element carbon in terms of hybridization. I want to start by looking at carbon's electronic configuration. Carbon, in its ground state, has an electronic configuration 1s2, 2s2, 2p2. But you know that carbon can be found in a compound such as methane, which is CH4, which tells us that carbon can form 4 bonds. How can carbon form 4 bonds if there are only 2 single electrons available in that 2p subshell? How can we explain carbon's tetravalency? That is, its ability to form 4 single covalent bonds, its ability to form a triple bond, or even a double bond. We say that carbon, in its ground state, can exist in an excited state. So I've redrawn my diagram just to show the pair of electrons in the 2s subshell and the 2 electrons we will find in the 2p subshell. For carbon to exist in an excited state, which I'm just going to call carbon star, one of the electrons from the pair, which is in our 2s subshell, is promoted from the 2s subshell into an empty 2p subshell. This will give us 1 electron in our 2s subshell and 3 electrons filled in singly into our 2p subshell. In total, we will have 4 electrons of equal spins, and these are 4 unpaired electrons or single electrons of equal spins. These 4 unpaired electrons, which are single electrons present in that outermost shell or valence shell, allows carbon the opportunity for hybridization to occur. We now have an s electron of a pure s character and 3 p electrons of pure p character. These pure atomic orbitals can then mix to give rise to a new type of orbital called a hybrid orbital, such that we can define hybridization as the mixing of pure atomic orbitals. These may be s or p atomic orbitals, such that a hybrid orbital is formed. These hybrid orbitals are of different shapes to the s or p orbitals, and they are all of equal energy. What is so special about a hybrid orbital is that hybrid orbitals, as compared to atomic orbitals, can give rise to a greater degree or extent of overlap in the formation of a molecular orbital, that is, during covalent bond formation. Let us look at the possible combinations of these hybrid orbitals which can occur in a compound containing carbon. So we have 1 s electron and 3 p electrons. If that electron in the s orbital, or if the s orbital mixes with all 3 of the p atomic orbitals, that is, we have 4 pure atomic orbitals mixing, we will get 4 hybrid orbitals. Because we mix 1 s with 3 p orbitals, we're going to get 4 sp3 hybrid orbitals. These sp3 hybrid orbitals are all equal in energy and shape. Let's say instead of mixing 1s and 3p orbitals, we instead mixed only 1s and 2p orbitals. This would give rise to a hybrid orbital called an sp2 hybrid orbital. Because we mixed 3 pure atomic orbitals in total, we would get 3 hybrid orbitals in total. That would leave 1 p atomic orbital unmixed, and this is what we see on the right hand side. So I'm just going to include my information for my sp3. Here we go. So I'm just going to leave my scope up to sp3 hybrid orbitals and sp2 hybrid orbitals, because the syllabus does not go into detail about sp hybrid orbitals. However, if you can guess, 2 sp hybrid orbitals are made by mixing 1 s and 1 p atomic orbital. Our focus is the sp3 and the sp2. You are to know which atomic orbitals are mixed to form these sp3 or sp2 hybrid orbitals and how many are formed. Using your definition of hybridization, you should also be able to define sp3 hybridization and sp2 hybridization. Let's take a look at our table. For sp3 hybridization, what we can see from the table is that in sp3 hybridization, 4 sp3 hybrid orbitals are formed. These sp3 hybrid orbitals are also considered to be orbitals such that when they overlap end-on with other atomic orbitals, they form sigma bonds. 4 sigma bonds around a central carbon atom leads to a tetrahedral shape. You should also know the bond angle for a tetrahedral shape, which is 109 degrees, or 109 approximately. With sp2 hybridization, which is formed from mixing of 1 s atomic orbital with 2 p atomic orbitals to give rise to 3 sp2 hybrid orbitals. These sp2 hybrid orbitals can also overlap end-on with other atomic orbitals to give rise to sigma bonds. 3 sigma bonds around a central carbon atom will lead to a trigonal planar shape. With a trigonal planar shape, you should also know the bond angle, which is 120 degrees. We are going to look at 2 molecules, 2 organic molecules, where one shows sp3 hybridization. This is ethane. and the other shows sp2 hybridization, and this is ethene. From this table, you can also see what their shapes would be and the number of sigma bonds they would contain, as well as the number of pi bonds. So let's look at them in detail in terms of the bonds surrounding the carbon atoms. Let's look at ethane. Ethane has a formula C2H6. So I'm just going to draw our structure of ethane to the side, which is how you would know it. And we can see 4 single bonds around each carbon atom in ethane. For carbon to form 4 single bonds, that means there needs to be 4 atomic orbitals overlapping with other atomic orbitals. In ethane, we will find sp3 hybridization, which gives rise, which gives rise to 4 sp3 hybrid orbitals. So each carbon atom will form sigma bonds with 3 hydrogen atoms, right? So each sp3 orbital will overlap with the s orbital of a hydrogen atom. This gives rise to 3 sigma bonds, which is 3 sigma carbon to hydrogen. And each carbon, or both carbon atoms, will bond to each other via the overlap of 2 sp3 hybrid atomic orbitals. If we look at this diagram, which shows us the atomic orbitals around each carbon atom, or I should say sigma bonds around each carbon atom, we can see each carbon, not hybrid, I'm looking at the hybrid orbitals around each carbon, I should say, where we see 3 orange looking hybrid orbitals around carbon. So those are 3 sp2 hybrid orbitals. Where each carbon bonds with each other, that's also another sp3 hybrid orbital shown in blue. Where carbon's hybrid orbital overlaps with the s orbital of hydrogen, we get 3 sigma bonds. Where the sp3 hybrid orbital of each carbon overlaps with each other, we also get a sigma bond. Let's say, for example, you were given a derivative of ethane called dichloroethane. Now, dichloroethane would have a formula CH2Cl, So it's as if we were replacing this hydrogen with a chlorine and this one with a chlorine. What do you think would be the shape and the bond angle in dichloroethane? In order to determine its shape and bond angle, we are looking at what type of electron pairs surround our 2 central atoms, our 2 carbon atoms. It would still be 4 bond pairs. That means dichloroethane, a derivative of ethane, would have a tetrahedral shape and a bond angle of 109 degrees. This brings us to our second molecule, ethene. Now, you would know ethene structure to be a double bond where each carbon atom is bonded to 2 hydrogen atoms. This double bond consists of a sigma and a pi bond. Can you tell me how or what that sigma and pi bond is made of in terms of the atomic orbitals that overlap to give rise to them? Let's take a look at our structure of ethene. In ethene, each carbon atom is bonded to 3 other atoms. So this carbon is bonded to 2 hydrogen atoms and another carbon atom. We say that in ethene, we have sp2 hybrid orbitals. These sp2 hybrid orbitals are formed from the overlap of 1 s atomic orbital and 2 p atomic orbitals. So this gives us 3 sp2 hybrid orbitals. 2 of these sp2 hybrid orbitals will overlap with the s atomic orbital of hydrogen. This gives us 2 sigma bonds, right, between carbon and hydrogen. The third sp2 hybrid orbital will overlap with the other sp2 hybrid orbital of the carbon atom adjacent to it. This also gives us a sigma bond. So we have 3 sigma bonds in total. Remember that in carbon, in its excited state, there would be 4 electrons of equal spins in the 2s and 2p orbitals. So we've used the 2s and 2 of the 2p orbitals to give us our 3 sp2 hybrid orbitals. And this leaves behind 1 pure p atomic orbital. In diagram 2, this pure p atomic orbital exists at right angles to the plane of the carbon atoms. So we see an atomic orbital which is above and below the plane or the sigma framework. These 2 pure p atomic orbitals via sideways overlap will give us our pi bond. So this is from a p-p overlap. Right, so our sigma bond between in our carbon-carbon double bond is from overlap of 2 sp2 orbitals, and the pi bond is from the sideways overlap of pure p atomic orbitals. I will attempt to draw my ethene molecule showing the orbitals. That is the orbitals which give rise to our sigma and pi bonds. So here we have our ethene molecule. And I'm going to mention the shape and the bond angle, where we have a 1s orbital mixing with 2 p atomic orbitals. That gives rise to 3 sp2 hybrid orbitals. The overlap of an sp2 and a sp2 gives us a sigma bond. We have 3 sigma bonds in total in our molecule. So that's carbon to hydrogen, and carbon to carbon. The p atomic orbitals via sideways overlap give us our pi bond. So here in our double bond exists a sigma and a pi bond. Around our central carbon atom, we look at the bond pairs around it, and we're going to count our sigma and pi bond together as one bond in terms of how it influences the shape of the molecule. The electron pairs being so adjacent to each other in a double bond, we're going to treat it as one. As such, we're going to treat carbon as if it has 3 bond pairs around that central carbon atom. As such, this gives us a trigonal planar shape. And this means I'm considering my bond angle as these 3. I'll just color it into a different color so we could see. So 1, 2, 3. So our bond angle here divided into 3 really gives us a bond angle of 120 degrees. And this is sp2 hybridization in ethene. also considering or looking at its shape and bond angle. Even though ethene has this trigonal planar shape where we have a bond angle of 120 degrees, I am going to mention what is the effect of this pi bond, this electron density, which is perpendicular to the plane of our carbon atoms. So yes, we would expect a bond angle of around 120, but technically the correct answer would be to mention that this bond angle influenced by that pi bond is going to be a little less than 120, maybe around 117 degrees. However, the general shape of ethene lends itself to trigonal planar, where our bond angle may not be exactly 120, but slightly less, given that the pi electrons, or that pi bond, that high electron density in that pi bond is going to cause a little more repulsion among the bond pairs to create a bond angle of a little less than 120 degrees. So to recap, in this video, we've looked at hybridization in terms of ethane and ethene. In another video, I'm going to look at hybridization in benzene and resonance.